Hello everyone, my name is Jeffrey Crane, and today we're going to be going over stress, strain, and the modulus of elasticity. Here is a table of contents of what we will be going over with going over stress, strain, and modulus of elasticity. So why are we discussing anything about stress, strain, or the modulus of elasticity? Well, while statics focuses on the forces outside of an object, strength of material focuses on what happens inside of the object due to the externally applied forces. The internal reaction of the body includes changes in the internal structure of the object, so that objects that were once thought to be rigid and static undergo stretching, shortening, twisting, and or bending. So what is stress? Stress is the internal resistance of a body or a member to an applied force. So when a force is distributed over an area, like the object below, the object must develop an internal resistance such that it does not break apart. The internal resistance that develops is called stress, and it is the internal reaction that counteracts the external force. Simple stress, also known as direct stress, is broken down into two categories: axial stress and shear stress. Axial stress happens when an object is placed in either tension or compression. When the pulling or pushing on an object, the area which develops the stress is typically considered to be perpendicular to the direction of the applied forces. For shear stress develops when an object is being subjected to external forces that are trying to shear or tear the object in two pieces. When shear stress develops, it occurs on the area parallel to the applied load. Here we see the simple stress formula, which can be used both for axial or shear stress cases. The formula is as followed, where sigma stress is equal to P, the externally applied force, divided by A, which is the resisting area. The units of stress underscore the difference between stress and force. Stress in force divided by area, while the force is the total force on the object. Recognize that stress and force are different, and not just because they're two different words. Here in example 1, we'll be going over axial stress. A tower crane lifts a load weighing 8,000 pounds. The cable used in the hoisting mechanism is 1 inch in diameter. What is the stress in the cable? Note, the stress in the cable is a tension stress, as the load it is lifting is pulling on the cable. So first we have our simple stress formula, which is sigma equals P over A. As the area is the diameter of a cable, we will be needing to use the cable's diameter formula, which is pi over 4 times the diameter squared. When we plug everything in, we get 8,000 pounds divided by pi divided by 4 times 1 inch squared. When we get the final answer, it is 10,186 pounds per square inch. Here in example number 2, we will be talking about shear stress. The two plates in the connection shown below are joined by one bolt having a diameter of 3/4 of an inch. If the load P is equal to 2,000 pounds, what is the shear stress in the bolt? Note, the shear stress in the bolt develops in a plane where the two plates touch. The load P, 2,000 pounds, is acting to shear the bolt at this location. So the bolt develops a stress to resist that. So we will use the simple stress formula again, where sigma equals P over A, and then again for the area of a cable, it is pi over 4 times the diameter squared. When we plug everything in, 2,000 pounds divided by pi over 4 times 3/4 of an inch squared equals out to 4,527 psi. As a quick note, in the previous example, a connection was shown where two plates were joined together. This is commonly referred to as a lap joint. This three-plate connection is sometimes referred to as a butt joint, and it is assumed the plates resist 1/2 the load carried by the middle plate. One item that should be noted about this three-plate connection is that each plate has two shear planes. If calculating shear stress for a bolt in this type of connection, one would have to multiply the area of each bolt by 2. Materials are always thoroughly tested by industry organizations or private companies so that we know with high certainty what the stress is that will cause the material to fail. Once the failure stress of a particular material is known, a safety factor can be applied to provide designers with an allowable stress. If the allowable stress is lower than the actual failure stress, then the material is of safe design. Allowable stress equals failure stress divided by the safety stress. In example 3, a cable on a crane is supposed to be able to lift the maximum load of 100,000 pounds. The allowable stress for this cable is supposed to be 60,000 psi. What should the minimum diameter of the cable be? Using the stress formula, we find that 60,000 psi is equal to 100,000 pounds divided by the area. To find the area, we just simply maneuvered the equation to have 100,000 pounds divided by 60,000 psi. With that, we get the area of 1.67 inches squared. However, the area of a cable is pi divided by 4 times the diameter squared. To be able to get the diameter, then, we have to square root 4 times 1.67 inches squared divided by pi to get 1.4746 inches as our diameter. Strain is when an object is loaded axially, it develops stress and begins to deform. Deformation is the total change in length that an object undergoes, i.e. getting longer or shorter. However, sometimes it is better to express deformation in a unit basis, and this is referred to as strain. Strain is the deformation per unit length. In the strain formula here, epsilon equals delta divided by L, where epsilon is the strain, delta is the deformation or change in length, and L is the original length of the object. In example 4, a column measuring 10 inches by 10 inches is supported by a concrete footing measuring 3 foot by 4 foot. If the column was originally 120 inches tall and under load it was found to be shortened by 0.008 inches, what strain did the column experience? Using the strain formula, epsilon equals delta divided by the original length, we put in the delta, the deformation of 0.008 inches divided by the original length of 120 inches, we come to find out that the strain was 0.000067 inches per inch. Hundreds of years ago, the relationship that existed between the stress placed on an object and the corresponding strain that occurred was observed and quantified as a material property known as modulus of elasticity, where E equals stress divided by strain. Modulus of elasticity is important because it gives one the ability to predict the behavior of a material under various values of stress. With the known value E, designers can determine what amount of strain or deformation should occur under a particular amount of stress or load. This is very important to know when figuring out how much beams and floors will deflect. A good way to think about a modulus of elasticity is that it represents one component of a member's stiffness or rigidity. When you compare the modulus of elasticity of steel to aluminum in the figure shown to the right, you can see that steel's E is larger by a factor of 2.9 times. What this means is that the member made out of steel would be 2.9 times stiffer than a member made out of aluminum. Finding the deformation that will occur under a certain amount of load or stress is an important ability. This can be done by manipulating the modulus of elasticity formula shown below. Where the modulus of elasticity equals stress divided by strain, you can move it all the way out to find deformation, which is the amount of the applied force times the original length divided by the area times the modulus of elasticity. In example number 5, a surveyor's steel tape is standardized to be exactly 100 foot when experiencing a pull of 20 pounds. If the pull on the tape is increased to 40 pounds, what is the change of the length in the tape? Note, the tape's cross-sectional area is 0.015 square inches and the modulus of steel is 29 million psi. Using the formula before for deformation, where the applied pressure times the original length divided by the area times the modulus of elasticity, plugging all those numbers in, we come to find that the deformation with the extra 20 pounds is 0.055 inches. The stress-strain relationship of a material goes further than just the knowledge of the modulus of elasticity. The plot of the stress versus strain is called a stress-strain diagram, which contains an enormous amount of information that is important to designers. Although all the materials will show different stress-strain relationships, an idealized stress-strain diagram for steel might look like the one that is shown below. The yield point and the corresponding yielding stress, Fy, represents a limit state of yielding, which is when a strain in a member begins to rapidly increase with little to no increase in stress. From the origin point up to the yield point, the material stress to strain relationship is fairly constant, as noted by the linear nature of the graph. As the curve goes past the yield point, it begins to see stress increasing up again to a maximum value called its ultimate tensile strength, a stress value referred to as Fu. Finally, we'll discuss some common construction materials. Steel, an alloy, is an alloy primarily made of iron. Iron makes up approximately 95% of the steel we use in construction, and the modulus elasticity of steel is again generally taken to be 29 million psi. The minimum yield strength for steel varies from 36 ksi to 70 ksi, while the ultimate tensile strength varies from 58 ksi to 100 ksi. Concrete is the most common building material used in the world today. It is a mixture of Portland cement, water, sand, gravel, and potentially some admixtures. When people discuss the strength of concrete, they are typically referring to its compressive strength. A rule of thumb is that the tensile strength of a concrete will be roughly 10% of its compressive strength, and the modulus of elasticity generally range from 3 million psi to 5 million psi. Wood is a very common building material in many light construction applications. Wood strength will vary depending on the type of behavior, but it is generally good in bending and compressing parallel to the grain while being fairly weak in shear. Values for the modulus of elasticity of wood actually exist in all three directions, although the modulus of elasticity in the longitudinal direction is the value that is typically referenced. Values for the modulus of elasticity vary based on the species of wood, but it generally ranges from 1 million psi to 2 million psi. Thank you very much. I referenced our textbook, and if there are any questions, please do not hesitate to reach out to me via email, and thank you for your time.